Alright, so you'll have to excuse the noise out here. I hope this isn't annoying. I'm gonna speak through this mic because my voice isn't like super loud. So hopefully you can hear it over all that noise over there. But yeah, so basically, yeah, I'm gonna go over like a lecture recap, and then before diving into our actual workshop. You might have noticed last week there was a bit of a disparity between what you learned in the workshop versus what you learned during the lectures, and that's going to be the case pretty much throughout, because the workshops are just to prepare you for doing your in particular like this week is like your preliminary site model, and then it'll prepare you to like go on site, investigate an area, which is what you'll have to do for your assignment, right? Anyway, so yeah, we'll just talk about theory. If you haven't scanned the QR code already, this is just a link to my notes. It's basically what I'm going to run through here. Sometimes I scroll through a bit too quickly, so you might miss some things. So yeah, if you just want to look at it on the side while I'm talking, you can feel free to do that. Okay, so basically, the idea with mineral properties, physical properties, is that you can get like a rock sample or a soil sample from site, bring it into a lab, get it fully like tested with like chemical testing and stuff. But the idea is this is very like costly in terms of time, in terms of money. So in reality, what happens is geotech engineers are trained to understand the physical properties of rocks. That's literally like how they look, how they feel, so that they can make pretty certain claims about what a rock might be and understand its like mechanical properties straight up, like without needing all this expensive testing, basically, right? So that's the point of your physical properties. Most of these physical properties are fairly straightforward. I'll mark down the ones that might take a bit longer to understand, but transparency, if you've ever used like Photoshop, opacity is like how see-through something is. So that's to do with light penetration. Luster, this one, there's a few things to understand about that. In terms of like how it actually works, it's to do with like the refractive index and the absorption of your rock. But there's just general and broad classifications that rocks are just grouped into. So you'll see here, there's like your metallic lusters and then glassy, dull. You'll hear a few other words like earthy, pearly, whatever, but generally the main ones that you'll see over and over again is like vitreous, which means glassy, dull or metallic, right? Yeah, and I suppose the main things that determine this is the minerals within your rock. So remember, rocks are made up of various minerals. That mineral makeup will determine, I'll get into some examples later, but that will determine kind of the look and like the vibe of your rock, basically. Yeah, and also impurities. So for example, quartz, the mineral, has a glassy luster. So yeah, you can just imagine it's glassy. But sandstone, when it becomes cemented, actually has a dull luster. So that's due to the impurities of the cementing materials in between. Yeah, hardness. So if you've heard of Moore's hardness scale, that's like scratch resistance, basically. So like diamond can scratch anything, basically. Then whatever hardness of 9 can scratch anything of 8 and below, etc. Yeah. You can remember that one like in like spy movies or whatever. They use diamonds to cut through like glass or something to rob a bank. I don't know, to rob a vault. Color's pretty straightforward. Streak is a bit different to color. Streak is basically when you crush up the rock, it might have a different color to its actual color that you see. The color that you see might be affected by like oxidation and other processes. So like for example, fool's gold is a mineral called pyrite, and that one has I've written its color is gold, like the appearance is gold, but when you crush it up, it's actually black. So it has a different streak to color. So crystal forms and mineral habits are different things. You can think of it like microscopic. This one might take a second to understand. You can think of it like your crystal forms are like small scale, how the crystals individually form. But your mineral habits is when you're talking about your actual minerals, like your feldspar or whatever. That's like how the crystals then form and become the minerals. So in terms of hierarchy, crystals small scale. In terms of minerals, habits, it's bigger scale, right? So basically, cleavage has two components. There's your direction and the quality of the break. So the idea of cleavage is when you try to break a rock, it might have a predictable plane of weakness, like on a chemical level, like chemical bonds and stuff like that. So here I've got a few examples. Feldspar you'll see come up a lot. This is like a two-directional cleavage, so there's two planes of weakness, basically, and so it's predictably will break along those kind of lines. Calcite has three, so it'll break into these kind of like cubic chunks in a predictable way. In terms of the quality of the break, you might hear perfect or good or indistinct and distinct, but the most important thing is the directions, to be honest. Right. Magnetism. The main thing to note is just that there's a couple of minerals that are magnetic. So this is a dead giveaway on site. If you put like a compass next to it and it affects the compass, that you'll know you're dealing with one of the magnetic minerals, right? Tenacity, elastic properties. You've heard of brittle, ductile. Malleable is basically, I'll tell you the difference between ductile and malleable. So a ductile material, like the definition of a ductile material is how easily it's drawn into a wire. So like copper is easily turned into a wire, basically. But a malleable is like you can bang it around with a hammer and reshape it easily. So that's what gold is, right? Yes, subtle but different. Luminescence is that it will emit a light when absorbing energy, basically. So there's very few minerals that do that, but that's again a dead giveaway if you know you're dealing with that mineral. If you remember your soil mechanics, there's your specific gravity that they might refer to, and that's just the relative. That's like the density relative to water, right? So like quartz sand, for example, I remember this number, 2.65. So that's because it's 2.65 times heavier than water, basically, right? Yep. Here they write that quartz and feldspar, all these various feldspars, average out to be about 2.65 as well. Yep. Does anyone have questions about mineral and material properties? Mineral and physical properties? Okay, so the minerals themselves, quartz we've brought up before. This is the one that primarily makes up sandstone. It's incredibly chemically resistant, and it has like this kind of crystal structure. It basically doesn't have a cleavage direction because it doesn't have a plane of weakness in the structure. There's not much more to talk about with quartz. It's got a very simple chemical makeup as well. Okay, your feldspars, right? This gets a bit more complicated. So the idea of feldspar is they're called aluminum silicates, right? Which implies that they always have aluminum, silicon, and oxygen. But what type of feldspar you have depends on these other three things. Okay, so there's potassium, sodium, and calcium as like your three ends of this triangle. Here there's like a big gap in terms of these can't exist because they're not chemically stable, right? It's called the immiscibility gap. And then along the top here, orthoclase feldspars is analogous to having high potassium, basically, right? Whereas your paleo-clase feldspars, it's on a spectrum between having like more sodium and more calcium, right? So you might hear Na Paleocose feldspar or Ca Paleocose feldspar, right? Yep. So as we saw before, this had a two-directional cleavage, so that was like the planes of weakness looked like that. Whatever. Yeah, that's pretty much it. I've got some examples here for you. So granite might be like an orthoclase feldspar. So these feldspars are minerals, right? Granite is a rock, but it has a high portion of these types of minerals. That's what I'm trying to say. And albite, basalt, your examples for Na Paleocose ones and Ca Paleocose ones, right? Does anyone have questions with that? Okay, so micas are getting a bit more complicated. So basically you have your black mica, which is called biotite, and your white mica, which is called muscovite. Yeah, so the biotite is like, it basically is rich in iron and magnesium, but let me just show you the chemical makeup of it. So it basically has iron and magnesium in it, but it's not primarily consisting of iron and magnesium. It's actually not mafic, right? Mafic, again, referring to things which primarily consist of magnesium and iron, but anyway, you'll see that a bit more later. But yeah, anyway, so your muscovites, yeah. Okay, let me just take a step back. Basically, the idea is these ones are like kind of sheets, right? So they have one-dimensional cleavage, so they have one plane of weakness. Yeah. There's some more details I've included here, but you can see this more in the igneous rock section when I talk about this more. Should make more sense. Your carbonates, should be a 3. Your carbonates, there's a bunch, but you'll mainly be focusing on calcite and dolomite. Calcite is the main ingredient in making limestone, right? And dolomite, there's a similar one called dolostone. Dolostone has calcite and dolomite in it, whereas limestone primarily consists of calcite. What else is there to talk about? It's highly reactive to acid, where it undergoes a chemical reaction and releases CO2, basically. So yeah, in your cement production, we use lime, which is calcite, essentially. And it's really, really bad for the environment because it releases heaps of carbon into the air during the production of cement. That's the idea. Yeah. Is there any other questions? No. Okay, so your rock cycle, we talked about this before, but I just want to touch on a few things. By the way, if you look in the lecture notes, you'll see a black and white version of this image. If you look through Kurt's PowerPoint slides, you'll find the colored version, which I think is more useful. That's this version here. Just because like everything's better color coded and stuff like that. The main thing I want to talk about is where you'll find each type of rock. So sedimentary rocks is from sediment deposits, and then they have to be lithicated, compacted to form the stone, right? And so generally what happens is it goes from like high altitude to low altitude areas where the soil gets transported due to wind, due to rivers, whatever. And then you might find sedimentary rocks at the bottom of the ocean or whatever. And then, and then if this is an area of regional tectonic activity, such as this oceanic continental plate convergence, then you'll find this is where your regional metamorphism happens, which is basically high heat and pressure. And yeah, you'll see that more when I talk about metamorphic rocks, but that's roughly in this diagram, that's where you'll find those type of metamorphic rocks. And then you have your oceanic plate that's being subducted here, and then it goes towards the core of the Earth. The plate melts, and then there's this plutonic region, which is just like an underground magma chamber. And then that magma chamber causes all this rock around it to metamorphosize. That's called contact metamorphism. And that might cause a volcano at some point, leading to extrusive igneous rocks. But if that, if the magma cools down and doesn't like reach the surface, it becomes igneous rock. So that's your intrusive igneous rocks there. Yeah. Does anyone have questions? That's roughly how it goes, right? You might see this in the midterm. This is a pretty common diagram that they want you to like list where you find all the types of rocks and explain why. So yeah, just keep that in mind. Oh yeah, you got a question? Oh yeah, that's right. So contact is the same thing as local, but that's a good question. So basically that's just high heat. Obviously there is pressure underground, but it's not the pressure from the tectonic activity. It's mainly due to the heat of the magma being next to it. Yeah. Do we have more questions? Okay, so let's talk about igneous rocks. So something you might want to write down is that felsic and mafic, they have like these names because this is ferric, which refers to right. Feldspar, that's correct. Silicon. That's of course. So the type of minerals that you find there, and then here's like magnesium. Here's ferric. So that's where your naming comes from. When you're using the words felsic and mafic, it generally refers to igneous rocks. Yeah, they're just like classifications of igneous rocks. Okay, and then here's some examples. This is a really good diagram. There's quite a bit to talk about. You might see that in older diagrams, felsic is called acid, and then mafic is called basic. But I wouldn't use those words. Yeah, essentially with your intrusive and extrusive, they're also called volcanic and plutonic respectively. These type of igneous rocks will have large crystals for your plutonic rocks, which basically have a long time to cool, so the crystals have time to get bigger. And your extrusive rocks have small crystals because the crystals have to basically stop growing very quickly when they touch the surface. You might also find that they're very porous, so they have lots of voids due to gas bubbles escaping. So I think that's the case for basalt, generally. You'll see that there's like a bunch of holes in it and stuff because gas bubbles, right, as it's trying to cool down. Yep, so those words that I was saying earlier, in terms of the minerals, you got your biotite and muscovite here, and your feldspars, right? So potassium feldspar is your orthoclase feldspar. Paleoclase feldspar, you have your Na-rich side and then your calcium-rich side, so that one's kind of a spectrum. And yeah, quartz. And these ones, I wouldn't worry about these minerals so much. You should know their names, but like they're not really touched upon so much in this course, for the mafic ones. Okay, so we're just gonna keep going. Your Stricken diagram, basically the idea is that the bottom part of this is not so important because pholloids are very, very rare. And so you just want to focus on this left part of the diagram here. This is referring to your felsic minerals, right? Whereas the red the one I've highlighted in red here, this is for your mafic minerals. So again, they'll use like your pyrozine and stuff like that. But more often than not, you'll be focusing on using the Shostakin diagram for felsic rocks classifications, right? We're still talking about using the Shostakin diagram for felsic rock classification, but here I've included a plutonic one, right? So that's when there's a lot of time for the rock to cool. Then you can see like you've got your granites and whatever else it says here. And but then here's your extrusive one. So instead of granite, it becomes rhyolite, right? For example. So that's when it has to cool quickly. Essentially, right? Yeah. Here there's detail and field. Detail just means that one's more detailed. Field just means it's simplified, right? Same diagram, right? Yep. Is that okay for everyone? Yep. Okay, we're gonna talk about sedimentary rocks. Yeah, bro. Oh, yeah. In the midterm, you'll be given the diagram. You'll be given the shape of the diagram and everything. I think you'll probably bring in a ruler, and then you'll just. Actually, I'll show you what it looks like. Using the Shostakin diagram. So they'll literally give you the triangle already, and then they'll tell you a bunch of percentages for the numbers, and you just follow the steps. I would just run through one or two of these practice questions before your midterm, and it's the same thing every time. Yep. Okay. For sedimentary rocks, basically you have three classifications. You have clastic, chemical, and organic. So it's just about how they form. So clastic is basically, there's like a glue material and they stick together. So that's like sandstone, shale. Conglomerate's a new word, but it's basically just large size pebbles or boulders being glued together. And particularly conglomerate is your rounded ones. You might hear breccia. Breccia is your angular rocks, but they're both about boulder to pebble size particles. Okay, and then chemical is basically when it's crystallized from water, it's just like the precipitate, which becomes your mineral, right? So rock salt. I've included this one because in my head, like this visualization makes the most sense. So like rock salt is from a precipitate of water, and it just becomes like a salt. Organic is when it comes from like, so like coal, for example, is from dead animals and beings and stuff, and then it turns into a rock. And then limestone is, as I mentioned last time, sea creature shells and the sediment particles from that. So you might notice that limestone can both be classified as organic and chemical, and you'll find that across various websites you'll say either one or both. And that's because limestone can be formed as a precipitate mineral, but it can also come from sea creature shells and then become lithicated and become stone. Okay, does anyone have questions to do with sedimentary rocks? Here I've included a little diagram. You can look at that more on the Google Notes. Yeah, and the metamorphic rocks, the idea is around 200 to 300 degrees. If you heat up a rock to that kind of temperature, it starts to metamorphosize and become a different rock, essentially. So here is the effects of contact metamorphism, where you just have heat, so high temperatures. So like around a magma chamber, for example. And then regional metamorphism is where you have high temperature and pressure, and it's to do with like your large-scale geological events. Here you can see we have shale, which is your clay and siltstone being metamorphosized, and it turns from slate to phyllite, then to schist, then to gneiss, and then migmatite. And you can see this on this diagram. That's when you have your various orders of increasing metamorphic activity or rocks and stuff, right? Yep. That's pretty much all my notes. So I'm gonna get you guys to do a quiz. Okay, so let's explain these answers. Yeah, I remember I made question 2 and 3 quite hard off the top of my head, so that makes sense that it went down for a second. Yeah, so the idea is with sandstone, I know it's in different bedding layers, but in terms of like the chemical bonds, there's actually no planes of weakness. So you'll see that sandstone can chip off in, like it doesn't have a predictable chipping pattern. Do you know what I mean? So, wait, let me draw it. See, I'll draw it on the whiteboard. So although sandstone might be formed in like bedding layers like this, right? And you can see the patterns on it. If you split it in half like that, it's just going to look like that, right? It's going to be bumpy. It's not going to be a particular like plane of weakness or anything like that. So cleavage is about the break, right? Yeah, so basically conglomerate is boulder sized particles, but so is breccia. So I draw that up. Yeah. Yep, so breccia and conglomerate look like this. I have a question for you, right? So if breccia gets weathered, like its sides get all like rounded out, right? So instead of having like angular, subangular particles on the outside, it just looks like that. Is it still breccia or is it conglomerate? Exactly. If you split it in half, you'll find that it still looks like the inside has all these angular shapes. So it's still breccia, right? Yep. Okay, so basically this is just like, let me zoom in. So orthoclase feldspars. Remember, that's your potassium feldspars. So I said rhyolite. So this diagram looks a bit different to the one that I was showing you before. But the idea is the rock names are up the top here, and the texture is to do with how small the crystals are, and that's due to the cooling time, right? So rhyolite is still over here. Rhyolite has the highest amount of potassium feldspar, basically. Yeah, so the idea with muscovites here is they're not actually included in this particular graph, and they're generally associated with metamorphic rocks, such as schist and gneiss. So actually, one way they get white maker is from clay minerals being metamorphosized, right? That's the idea. Yeah, so this is just like, if you remember the names, basically. So migmatite is the one that looks like this. it's at the very end of the increasing pressure and temperature, and you'll find it lowest to the core of the Earth. So. And this one's interesting because I actually didn't know this until I just like dug around last night to make this quiz. But Hornsfels is really interesting because it's made from the same like makeup as, for example, shale and schist. Oh, sorry, as schist, but shale will become schist under regional metamorphism, whereas it'll become Hornsfels under just the contact metamorphism, so just heat. It's not really a good example here that I can find. That's not a great diagram. Is this it? Yeah, here. So this shale layer, when it's near the magma chamber, is Hornsfels basically. It becomes Hornsfels. Quartz becomes quartzite. I mean, quartz sandstone becomes quartzite. Limestone becomes marble. Right. Generally, these quartzite and marble are associated with contact metamorphism, not regional. But yeah. Okay. Yeah, we'll take a short. Oh, okay. So let's look through these. Feldspars, Troy's coal. Yeah. Anyway, see all your wonderful drawings. Good to see that we have more of a variety this time. Okay.